So we'll be talking about how to prepare calculations for checking and approval, and we'll give some tips about computer modeling and analysis. And then the big issue is how do we check these calculations, and some tips for checking drawings as well, because often somebody else will be checking them as well as you, and you need to make sure that in a state that is fit for checking as well. I say it may contain British humour because, well, I'm British. And I'm feeling very patriotic this weekend as we've just crowned a new king. So God save the king. So a recap from seminar 1, if you can remember that far back. We've gone through the concept design and now we're into the detailed design. Questions you need to ask before you jump into the detailed design is a solution stable, practical, fit for purpose, robust, economic, and does it meet the brief? If it does, then you can go on to detailed design. So the seminar tonight is split into 2 halves. First is about preparing calculations, and the second half will be about checking calculations. So here's a simple example. You've got a floor plan of a building, and you've got steel frame, column in each corner. So how do you calculate the loads on each of the columns? Does it need to be any more than, well, you've got the loading there, 2.0 plus 2.5 multiplied by 4 by 3, and then you get 54. And that's often the kind of level of calculations I get to check. And then I mark them as 54 watts. Put the units in at least and give a reference to where the load is. So this is the loading within column 27, so therefore you're looking at a floor loading in kilonewtons per square meter multiplied by a loaded area 4 meters by 3 meters, which there gives you a load of 54 kilonewtons. So here's a nice simple example. Design a beam. It won't take you long at all, as somebody will come along to say. However, you need to know a few things before you design a beam. Obvious thing is, you're a commercial company. What's the job number? What's the job name? When does the information need to be provided? What's the job fee? Because the job amount, the job effort will be in proportion, or should be in proportion, to the fee acquired. What is the output that is required? Is it a simple 1-page calc, or is it a full design report? What design codes and standards are you using? Is it going to be steel, concrete, timber, or something else? More importantly, where is this beam? What's its span? Where's the load coming from? Is it static or dynamic? And what are the support conditions you need to consider? And what's the purpose of the beam? What is the beam doing? Which can make a big difference to what design you do. Are there limits on the deflection or other serviceability requirements for the beam? These all need to be stated, and of course the importance level. Well, we're in New Zealand, so typically you'll be working on ordinary buildings which are going to be importance level 2. So let's fill in some of those missing points. An example, a job name of Springtime Towers and a job number of 12345. Why not? Now, obviously, the client will want the information back as soon as possible. And the fee is a miserly, I've done pounds, but it could be even worse at $300. Well, we want some calcs and we want some sketches for my measly $300. What design codes and standards are we using? Well, we're in New Zealand, so your loading is going to be 1170. And if it's steel, we're going to put it at 3404. Materials, we've said steel, it's going to be on the first floor. The span of the beam is 8 meters. The loading is, well, it's residential and it's supporting a width of 4 meters. What are the support conditions? Well, it's simply supported on masonry walls. It's there only to support gravity loads, so there's no lateral stability required separately. For the deflection requirements, for example, in this case, it could be span over 360 or a limitation of 14 millimeters. And it's an ordinary building, so we call an IL2. So you're providing some basic information. This basic information should end up in your design features report. Now we're going to something more complicated. we design a frame. Now, frames are a bit more complicated, so you will be tempted to go straight for a computer. But wait. You need to think about the calculation production process before using a computer. So coming back to seminar 1 again, we gave you some golden rules, and as I say, the customer is king. However, the customer is not the structural engineer, won't understand the codes and practices we use. But good idea is to keep it simple. So bear in mind any complexity you put into this beam design or frame design is going to be expensive. And if you're designing a big building, there will be lots of things to design. So don't design every beam. You just select typical beams, usually a main primary member, a secondary member, and possibly an edge beam. And then you repeat that all over the building and at each level. By all means, use load span tables. That will give you a good idea of what sort of beam you'll be looking at, and use the company templates. Now, Redco has a number of company templates for designing beams and frames and all sorts of things. They're the lovely spreadsheets you're used to. Oh, don't forget that buildings move, and so you need to accommodate movement, and that may mean control joints in your masonry walls, or it may mean movement joints in various concrete slabs, or even a seismic gap if you've got a big enough structure. And it's not about minimum weight. You need to maximize the performance in terms of the economy. And don't forget the connections. Sometimes the connections will drive the design in this. So again, harking back to our first seminar, if you view calculations as a production process, and you've got some input and you've got some output and you've got some controls and mechanisms. This is a very fancy way of looking at an activity model, but the input would typically be the geometry, the loading, and the assumptions that you need to design your beam. The output obviously is calcs and sketches, and the controls are things like codes of standards, regulations, reference books, manufacturers' data, safe load tables, all those are controls. Those are things you can use. And then the mechanism is you. You are the primary mechanism producing this. You are producing these calculations, but you'll use tools. It could be pen and paper, or it could be advanced computer software. So what's the trouble with computers? Again, from seminar 2, persons with adequate structural engineering knowledge or training may carry out structural analysis. So you've got to bear in mind that analysis is different from design. There's often, or can be, a gap between the design initiator and the computer programmer. So the people writing software are programmers. They tend not always to be engineers. Usually the best technical programs are written by engineers, but they're not always the best interfaces. And that will remind you, what are you analyzing? Are you analyzing the right thing? Sometimes you're using a program out of context and you don't know. You're out of the scope of the program. Now, good computer software should tell you that it's out of scope, but many of them don't. And the checking process for the original software may not be sufficient. There are limitations. Every program, every computer piece of software will have limitations on its use, but they're not always obvious. So, as I used to say, we used to like to say, to err is human, to totally fuck it up, you need a computer. And this is a classic case of a total fuck up. This was a very expensive oil platform, and they did very advanced analysis using finite element analysis, but got it wrong. And the short answer is the FEA mesh was the wrong size, and it failed with a loss of $700 million. And hopefully nobody will make that sort of loss again, but it can happen. It happens to the best engineers. So coming back again, a reminder of seminar 2, 2D versus 3D. So I always start with 2D because most frames will be analysed satisfactorily as two-dimensional models, because most buildings are rectangular, certainly the buildings that most of us will be working on. So the advantages of 2D, it's much simpler for a start. It allows rationalization and repetition in the real structure. So that pushes you towards economy. in your structure. If you repeat the same elements over and over again, the building will be simple to build and cheaper to build. It also makes it much easier and cheaper to design. So avoid the complexities if you possibly can. Avoid complexities of out-of-plane member behavior. And don't forget, if you're using things like steel profiles, these are intended primarily for bending about one axis. So make it work the best way it was intended to work. But don't forget the third dimension, obviously, and the fourth and the fifth dimensions. Now, the fourth is going to be time, and the one that Einstein forgot was cost, being the fifth dimension as well. So we reminded that the amount of effort you put into your analysis and your design has to be proportional to the fee that you're charging as well, but it'll also be constrained by the amount of time you have available. So if you're going to build a 3D analysis model, think about what's required from your model before you start. Don't overcomplicate it. Try 2D subframes before creating the 3D model. So once you get into a 3D model, you really should have a good idea of how the model behaves before you get into it. So you should have a good idea what the answer is before you ask it. So for multi-story buildings, create one floor first. Add all the member properties, add the supports. I say no releases just yet. So apply a self-weight load case and then run the analysis. So that's your first pass. And if it doesn't work for that, you've obviously got something wrong with your initial model. So if there are errors, check what input you've got. Quite often you've missed some support somewhere. And does the bending moment diagram, the shear force diagram, and the deflected shape of the structure, do they look right? Are they as expected? So if you're putting a self-weight load case on a structure, you'd expect beams to sag downwards. Is your model in equilibrium? That's the good test, and you can check with that on the loads you've put in versus the reactions you get out, and most of those will be vertical as well. So then you go through the next iteration. You start releasing supports as appropriate in a logical order, and then you can rerun the analysis at each stage. Avoid trying to release everything all at once because you'll find your errors and then you won't find your errors. Errors will come up and then you'll wonder where the hell it came from. So 2D models are much simpler because you've only got 3 degrees of freedom to play around with at each support and at the ends of each members. However, 3D models have at least 6 degrees of freedom, or 7 if you're German. The Germans and bridge engineers alike like to think about warping, which is way too complicated for us mere building engineers. So add members and releases as appropriate in a logical fashion. Now you're building up this model stage by stage. And as you run the analysis, you'll be able to debug the program as you go. You'll notice that when you start moving on to lateral loads, you'll find more errors because the behavior changes. And watch out for fully released members in 3D frames. So if you do a torsional release at both ends, you'll end up with a member that's spinning. You need to restrain it. Add the other load cases and rerun the analysis at each case. So you're checking and checking as you go. Add load combinations and then rerun the analysis at each stage. I know it's sounds a bit long-winded, but if you jump in straight, I'm going to do all the loads, I'm going to do all the load cases in every member and every release, and then it falls over. You've got no idea where it's gone wrong. By doing it in a sequential manner, you can pick out which stage has gone wrong. So do some sense checks. Do the reactions equal the sum of the applied loads? Add the rest of the floors and the rest of the frames. And don't forget, don't ignore these errors. Your software, particularly frame analysis, will throw up errors. So there could be a singularity in your matrix, which sounds very sci-fi, but basically means that it will not converge and you don't have a stable model. If you don't have a stable model, you're not representing a real structure or at least the structure that you want to build. There's in multi-frame, there is an option to click ignore tension only members and then run the analysis. And suddenly you'll find your frame is much stiffer and your deflections are much lower. But that means your cables are taking compression, which is a mistake. So in summary, the do's and don'ts of producing your calcs. And as I say, don't present fact pack calcs. That's quite an old expression now. Back of the envelope calculations, as we used to call them. So write them up properly and present them in a fit state that they can be checked and submitted for building consent. If you do hand calculations, and I'm sure you're all advanced enough now not to do hand calculations, and at least doing hand calculations in MathCAD, if you do hand calculations, then scan them in, save them to the project folder, and include them in the calculation report, probably as an appendix. So what you'd like to do, and what I'd like to do, is produce a standardized structural calculation reports. Now, this is what Redcode does. We've got a lovely template for producing a standardized structural calculation report. And within that report, we can put our standardized calculations from all those lovely Excel templates we have. We've got a collection of standardized details and drawings in our CAD library. So if you need to pass it on to somebody else can pick them up and modify them, and they know where they've come from. They can understand them. If you start everything from scratch, then the next person has to start everything from scratch. The big important message is start your design features report before doing any calculations. Now, many people regard the design features report as an afterthought, and they've done all the calculations, then think about, oh, I need a design features report to submit for building consent. And then they're scrambling around. If you set your sights on a design features report at the beginning, you write that, you get it reviewed, and that should set out the scope of your calculations report, the materials you're using, your codes and standards, how many different elements you're going to calculate, and so on. It will also provide your references, including your geotechnical report, references to your architectural drawings, and so on. Okay, so we've done our calcs. Now, are we ready for checking? So, part B, checking calculations and drawings. So again, a recap from seminar 2. Validation, V&V is validation and verification. Validation, are we modeling the structure correctly? So do the numbers add up? Verification is more of an engineering thing. Are we modeling the correct structure? Are those nodes you've put in there and those elements you've put in there, are they really representative of the connections and members in that structure? Are the restraints you put in real boundary conditions? So the first half is a software issue, but the second half is definitely an engineering issue. And if you've got proprietary software, they should have already done this. If you've made up your own software, or you're using company-derived software, then this may still be a thing to check. In terms of calculations, now different companies will have different approaches to it. Here at Redco, we'll say the lead senior engineer or the practice manager, or maybe even the project manager, will decide what category of calculation check is needed. And this should be decided at the initial project briefing stage. So you need to set out before you do the calculations how much deep checking, what level of checking you need. So category 0, it's no check required if it's carried out by a suitably experienced senior engineer. So that usually excludes graduates. So if you've been doing engineering for quite a number of years, you can possibly do some minor elements without them being checked by somebody else. Category 1, then just a conceptual check. Have a check on the basic structural principles, what load cases and so on, and it's usually by somebody else in the same design team. Category 2, you do a full structural check, usually by another engineer in the same office. So this is all internal, and all part of your internal QA system. Now, category 3, now if you've got a special structure, category 3 should be done by somebody else outside the company, which is a full independent structural check. In New Zealand, this could be a PS2. Now, the PS2 checks are done by another company, but they won't do a full analysis. They'll review your design, your calculations, and consider it reasonable as well. Now, PS2s, producer statements version 2, are more in demand, more and more in demand by councils, as councils have got less time and less technical ability to do complicated checks on anything that's more than a house. So what we're finding now is that if it's not a timber framed house or something similar to that, they'll often ask for a PS2 to be provided. So again, this is internal. Unchecked counts may be kept on file, but any drawings that are based on them basically should have a preliminary status. And they shouldn't be issued externally until they're checked by somebody other than the author. So when you issue them, you put them in the documentation issue subfolder. This is for the Redco guys. I'm sure other companies will have something similar. You have an issue folder of things that you have issued. So in this case, it's calculations. Levels of checking. Don't forget the most obvious one, self-checking. You need to check your own count. And it's amazing the number of counts that I see which have obviously not been checked by the person who's written them because they contain so many basic errors. At which point I throw them back to that graduate, say, do them again. So a review against a project brief, and it's a bit like, have you answered the exam question? Don't forget the checklists. Now, I developed this thing, which is a checklist for checking calculations. For the Redco boys, this is available on the common directory, common folder under graduate seminars and checklists. And this goes into quite a lot of detail, but which I'm about to go through in this presentation. There's look at the typical details. Beyond that, then there's peer review. You can check it by another graduate or by another engineer. And then we get into peer reviews. So we at Redco have a spreadsheet that needs to be completed by the engineer and the reviewer. So, yeah, we can pull that one up. You bear with me a minute. So this is Redco's checklist. There's some admin things to do, but here we jump into the engineering checklist. And again, for those boys in Redco, these have got to be filled in before the calculation report is signed off. And they're supposed to be filled in by the engineer and by the reviewer. So it's some fairly basic stuff. Have you got the title right? Have you got the job number right? Have you got the correct revision and titles and so on? And if you get the PS1 wrong, the councils can throw them back. So if you've got the wrong address or the wrong lot number, that can be sent back, which causes delay and embarrassment. So coming back into the design features report and into the more technical side of things, these are fairly high level things to look at. And then we go into the technical content, again, high level. Is it steel? Have you looked at everything you need to look at, and so on? And once you've completed all that, you can click on the yes, we've done the check, and you can ask for it to be signed off. So no sign off without that. So each project, once you've completed your calculation report and if necessary drawings as well, should have one of these checklists within the folder. It's part of our QA system. So drawings should be checked by another technician if available, or by a checking engineer. So the usual final review is done by the assigner of the job, and that's usually the lead structural engineer or lead technical manager. And that is a very high level review to see if there's any obvious things wrong with it. And the final review won't go into the amount of depth and detail that the peer reviewer will. Now, Yo-Yo back in Redco should be looking at these things and reminding you that these sheets need to be filled in. So a more detailed, more granular, fine granular level looking at calculations. So start with input data. Where has it come from? Have you stated the sources or have you just made it up? Obvious sources are the New Zealand standards, trade catalogues and textbooks. Give the references to the textbook if you've used one. Is each piece of input data actually cross-referenced? And have you supplied key plans? Is the data complete? Have the assumptions been applied and are they conservative? Once you've checked that, you can raise a list of shortfalls and reservations on the input data. And as I say, calculations are fairly meaningless without reference to key plans. So I often get calculations as, here is a calculation for beam 1 with no idea where that beam is. So once you're checking calculations, you need to be able to reference it or refer to a drawing to make sense of it. So if the calculation says it's 10 meter span, then the drawing should show me that it's a 10 meter span. Then we get into the number crunching. So have you used algorithms? Well, of course you will have done because you've taken formula out of codes of standards or even textbooks. Are they appropriate for calculations that you've presented? Are you working to the limits within defined? So don't forget, all standards, codes of practice have limitations on them. And so you'll be using standards that are defined for buildings. Be careful if you go off and try to use it on something that's not a building. Have they transposed it properly? So one of the big missing factors is units. Units are a missing factor. They will have forgotten to put in the units or will have put in kilonewtons where it should have been newtons. Oh, be careful of using American standards. They're all in imperial units and the transposition into metric isn't that great. Is the method of computation actually stated? Is it explained? So tell me what you're doing. So if I'm presenting with piles and piles of numbers, I need to be able to know what you're doing with these numbers. How are you going to calculate it? So tell me the story. So have you done these manually or have you used proprietary software? If it's proprietary software, say so. Say what it is. Is it Bentley multiframe or whatever? Is it Heatans? Is it something else? Or have you taken a spreadsheet? Now, is this a used spreadsheet that lots and lots of people have used? Or is it something you've just made up yourself? Or you've even been smart enough to write your own macro? You need to say those sort of things. And that type of thing, the bespoke macro, really should strike red flags into the checker. So if you've used this bespoke software, or if you've got an engineer who's writing his own macros, have they been validated for use? And how have they been doing it? And again, are they being used within the limitations of that macro? Again, list of shortfalls and reservations in your output. So we've done our input, we've checked the number crunching, and now we're looking at the output. Is the output clear? Is the result or the answer clearly shown and identified? I like to highlight it in yellow or red or green or whatever to make it obvious that this is the output of this calculation. And I also like to see things like OK, checked OK. And if you're running something like MathCAD, you can put in little if statements which will turn as to OK or no good as and when required, which helps you check enormously. If you're using Excel, you can use formatting, conditional formatting, which again can be either green or red, to depending on the value you're putting in to say whether it's okay or not okay. Quite often, the check is on the utilization ratio, so it's a measure of the applied load versus the capacity. So have they checked it? And is it 100% check, or is it something in between 0 and 100%? Are the outputs referenced properly? Is it going to be used for further calculations? Now, this is why it's very useful to highlight the output of your calculation and even give it references, because it's a nice bright green color. You know that's going to be used somewhere else. So when you refer back to it, you can find it easily. And don't forget the units. Many calculations go wrong with the units. That's one of the joys of MathCAD, actually, that it does handle units very well. And don't forget, most of the formulae in codes of practice and national standards are unit dependent, but they don't tell you that. And if you put those formulae in MathCAD, MathCAD will tell you that they are unit dependent. So, more about checking calculations. What are the big picture checks? Well, if it looks good, you're halfway there, basically. So is it obvious what this calculation is for? Is it obvious which project or which structure these calculations refer to? You've just got a load of handwritten scroll with lots of numbers on it. Oh, awful. Send it back. And I have sent calcs back in the past from a chief engineer who wrote a handwritten calculation which was illegible as well. So I sent it back. Have all the assumptions been stated? So are the calculations complete? Have the reference to the formula been stated? So if you're using a formula, where has it come from? Often it will come from a code of practice, but you need to say which one as well, and help me, give me what page or what clause or what table it's come from. If you're using values from tables, say what table it's from. That's very helpful. Is it logical? So is each step explained? So all engineers like logic and like to do things stepwise. One step follows another, follows another. So the output of the earlier calcs feeds into the input of future calcs as well. Looking at drawings for a moment, there's some big picture checks as well. So similar to the calculation report, is the purpose of a drawing or drawings clearly defined? Why have you drawn this thing? Have you written which project or structure the drawings relate to? Have you got the right job number on it, which is often goes astray if you're just cutting and pasting an old job? Does the drawing need to be printing out full size to be checked? Yeah, that's an interesting thing, because nowadays it's very rare to print out an A1 drawing to actually an A1 piece of paper, and they often get reduced, photographically reduced to A3, which in some cases can make them unreadable. So very be careful about how you're using small text, small numbers, and so on your drawings. If it needs to be printed out full size, it's worth saying that on the drawing. If it needs to be printed out in color, it needs to be stated on the drawing as well. So have all the dimensions been provided to be able to build this building? So the point of your drawing is to give it to a contractor so they can build the building. If you haven't got enough information on that drawing, he or she cannot build this building. It's also nice to have things that are hidden, like utilities and services and levels, existing and future levels as well. Don't forget, your drawings don't stand alone. They will be referred to by other people, and you will have to refer to others, such as the architects or M&E drawings as well. A good check, actually, on drawings, if it hasn't got all the information you need to build this building, you won't be able to redraw it from scratch, which means starting with a blank piece of paper. Now, quite often, many drawings are not based on Scratch. They are based on the architect's CAD model or somebody else's DXF file or DWG file, and then we build it up from there. And it looks lovely in the model, and you can manipulate it in the model, but there's no dimensions on it. Unless you've got dimensions on your drawings, you can't build it, Holly. Contractor can't build it. Again, use logic. Are they presented in a logical manner? So we start with general arrangements, then we go on to elevations, then sections, and then detail. So we're going from the whole to the particular, work from the whole to the part. So general to the specific, and get more and more detailed as the drawings go on. So high level, big picture stuff at the front, zoom in as you get further down the drawing list. Context. So the drawing's not much use without the context. And you need to know what the drawing was based on. Usually the drawings that you produce or your technician will produce are based on the architect's drawings. Sometimes will be based on, I'll put Ordnance Survey here, that's UK, or topological surveys. So a surveyor has come around and done a detailed CAD model which you can build your engineering on. If there are trial pits, boreholes, or geotechnical reports, worth putting those in as a reference in your general notes. If there are services, particularly hidden services, always worth putting them on your drawing, at least a reference to the drawing as well. Now, this is a funny thing, is there'll be conflicts between your drawings and somebody else's drawings, and it gets embarrassing when you find those on site. These need to be checked before they go for construction. Then you need to check whether you have fulfilled the design intent when doing these drawings. You need to compare them to the engineer's markup drawings. And there's often a gap between the engineer and the CAD technician or the engineering technician as to the engineering intent. And it's very difficult for an engineer who doesn't draw or a technician who doesn't do engineering to actually fill in the gaps. Detail checks. Again, we're going more and more fine-grained in the detail here. So there's obvious things like, have you got the job number on it? Have you got the name of the job? The date and revision, those are some very important things. Some of the most important things you can put on documents and drawings are the date. You need to fess up who's done it, who's checked it, and who's ultimately going to pay for it as well. What's the drawing for? So is it just for information? Is it part of the design stages, or are you actually setting out to build it as well? You should have the scale on your drawing, and I don't like seeing the words as noted under that scale box. So actually say what the scale is and what units. Now, if you're really good, you'll put a scale bar on your drawings, because people don't blow them up to the full size, they reduce them as well. Sometimes you'll have a specification for both the materials and the workmanship. So if you have, then refer to them. In many of our smaller jobs, the specification will be on the drawings. The specification could be on just the notes page as well. Again, refer back to the notes page in your detailed drawings as well. And if you're using proprietary products, so there's all sorts of proprietary products like reed bars and so on, couplers and casting fixings and Hilti manufactured components, then put them on and refer to them by their reference number. It makes them much easier to buy and purchase as well. So say what it's been, what the drawing has been based on. So parting thoughts, and this mirrors what I said in my investigation and inspection seminar. Take nothing for granted, and don't assume everybody knows what they're doing. So take nobody's word for it. Assume nothing. As I say, as Sensei said, shut your eyes to see what's not there. And sometimes you can look at something and you don't see anything wrong with it, but it's missing information. And check for inconsistencies. Do the drawings that you're producing actually match the calculations? So thank you for all that. That's the end of the presentation. Looking forward, in 2 weeks' time, our next seminar will be Wind Analysis to NZS 1170 Part 2. Now, this was a presentation I prepared a couple of years ago just for Redco. and then had to rewrite it because joy of joys, they brought out a new version of 1170 Part 2, the 2021 edition. So I'll be going through comparing older version with new version as well. And wind analysis seems to be where everybody trips up because everybody does a different version